Does he teach at Mount Laura, Paul? Is that where he's? Yeah, he's in MLA.
MLH, yeah.
It's just T. Presley at Alamo EDU. He doesn't have any numbers.
Check, check, check.
He responds to emails pretty quickly too. Before you majored in math, what did you plan on doing?
Let me get this turned on. Hey, everyone, we'll get started. Can you all see my screen and hear me and everything okay?
Yes.
Okay, all right. We're having a conversation here. We'll pick up in about 2 minutes. So I take the final, I take my work, I go out into the hallway and he's standing there and I'm like, here you go, sir. And I said, hey, I wrote the problems down. I want to go home and try them again. I just want to make sure you're okay with that. And he looks at his watch and he looks at my work and he's like, do you have some time to come to my office today? And I was like, oh shit, you know, so I went to his office later on and he sat me down. He's like, what's your major? I said, physics. And he's like, you know, his words is, he said that it would be an insult to the subject of math if I didn't pursue a math degree. That was his motivation to me. I thought I was in trouble or something, you know? Yeah. So he really influenced me to like, hey, just go down. Like if this Cal 2 was easy for you and you were able to finish that final in like, you know, whatever time it was, he's like, you should think about doing math. And so the physics classes, I was having trouble because they weren't making. There weren't enough people taking the classes and I would sign up and then it wouldn't make. And I'd be like, what the hell, man? Exactly. Well, the math wound up being the same way too. Yeah, but it was a little bit easier with the math. In grad school, that's where we ran into the biggest problem because in grad school, there was only 3 of us that got our masters at the same time. And so to make a classwork, we had to petition every semester and like maybe pick up 1 or 2 students and we'd have classes with 5 people, you know, and that was it. And So I wound up doing the math because he kind of steered me that direction. And then I just kept going. I enjoyed it. I was doing well. And so I was like, I wasn't even thinking about what I would do with it. I was just like, oh, let me just do math. Then I finished, then I did grad school right away. I finished grad school and I got my master's. It only took me 3 semesters. No, wait, hold on. I forget. No, it was a summer, fall, spring, summer, and I was done. So, and then by the time I finished grad school, I was already teaching here full time. Like I started teaching here full time while I was in grad school. And so by the time I finished grad school, I already had a full-time job. And I'm like, let me do this for a year or so. Because I had worked with 3 different companies for jobs after grad school. And they had like a job fair and I had, interviews and stuff. And I was ready to go into the, commercial stuff. Raytheon was one. There was, other ones. NSA was another. I don't think I would have got an NSA because my background was too bad. But anyway, so I decided, you know what, I'm just going to teach for a year. So I just need a break. This is kind of cool. I can kind of relax. And that was 20 years ago. It's just I haven't walked away from this because I enjoy it so much still.
Yeah, I feel like being a math major is one of those things that's like something you never think about.
Yeah.
Like high school or elementary, whatever, it's always like all the generic stuff.
Yeah.
And then you get to college and it's like, wow, there's a lot more jobs than I thought.
Yeah. If I could go back and stay in the math, I'd probably, if I was going to do the math again, but as a career to like make money, I'd probably have steered towards like actuary science because, actuaries, they make really good money, but I knew then I didn't want to like sit there and do that sort of work, All right, everyone, 9:02, let's get started. So today is an important day. We're going to talk Maclaurin. I don't know if I can wear this today because these different glasses fog up really bad. Today we're going to talk about Maclaurin series and Taylor and Maclaurin series. And I wanted to start off with something here. We're going to watch a YouTube video. It's very short. It's going to be hard to understand, so I'm going to translate this, okay? Okay, so here's the setting. This video is titled "Horrible Teacher." Let me make sure I'm sharing my sound. Okay, so this was posted a long time ago. It's got 500,000 views, posted in 2007. So this is a class at some college, I don't know where, and this some student posted this, I think, saying this is a horrible teacher. And I think this is a differential equations class, pretty sure. I haven't really looked at the work too much. So the students are having trouble with something and they're talking to the professor. I'm just going to play it and let's see what happens here.
It seems that you are not happy.
Why is the audio is not coming out up here? Hold on. Let me try something. Try that.
You are not happy with the series.
Okay, I have to
It
translate.
seems that you are not happy.
It seems that you're not happy.
You are not happy with the series.
You're not happy with the series.
How you multiply the series? But let's see
How you multiply the series.
now some other example.
I don't know
What
what
I
he's
can
saying.
do. Yeah.
Now say what you want about this professor, okay? At least he's recording his lectures back in 2007, I mean, that's something.
From that first line, how did you get from the first line to the second line?
You multiply.
So a student asked a question, you can't hear it, but he says, you multiply. The teacher answers, you multiply. And they all start laughing.
Show exactly how.
He said, can you show us, the student says, can you show us exactly how you did that?
Well, exactly how? Let's see.
Here we go. Here's the important part. So the professor's checking his notes right now. He's pre-written his notes before class. He's just checking to make sure he didn't write something down wrong, right? Because that can happen. So he's checking because the students are questioning him. Here we go.
From here to here.
Yes.
Students asking how he's getting from one line to the next, right?
Oh, you can divide one.
Oh, you divide one. That's what the professor says. Oh, you just divide one, all right?
No, that
Divide
doesn't
by
work.
one
That
doesn't
doesn't work.
Why not?
Could you do it manually? It doesn't work. It doesn't make any sense.
Okay, so the student's saying, can you do it? Like do it manually? It doesn't make any sense, right? And
Okay, let's go further.
Why are you ignoring my question? That
No,
doesn't make any sense.
you are doing this.
You don't answer anybody's questions.
Okay, let's go further.
all right, so this is a weird video because you can kind of look at it from two different perspectives. As a student, I think a student paying to go to school should be able to ask a question and the professor should turn around and legitimately acknowledge the question, right? But it depends, to me, it depends on the level of the question, right? So if someone in here were to ask me, hey, how do you take that derivative, right? I would be like, well, I'll show you, you know, it's Cal 1, but I can show you how to do a derivative. But if you're asking me how to factor a quadratic or use the quadratic formula, I'm gonna be like, come on, you know, like that's not for here. I think this professor is treating the question like the quadratic scenario. Like you should know how to do this. Like we can't waste time doing this, what the student's asking. So all the students are like pissed off in the comments, but then if you read the comments, it's like both sides. Some people are like, you should know how to do that step. And other people are like, oh, you know, I'm paying to be there. You should show me, right? So I'm not here to make any judgments here. My goal of showing you that video is that if you're ever in a class down the road and the professor's sitting there and there's a step that they show you and you don't understand it, I think you have the right to ask a question. But if the professor says you should know this already, that's on you. You need to go figure that out. You need, don't have the attitude of, well, it's wrong. I mean, the student was basically saying like, no, it doesn't, that doesn't work. And it's because he doesn't know how to take the number 1 and divide it by a series. Okay, we're going to do that today. We're going to see how you divide series together or divide something. So this is a preliminary concept that the student should have known that they don't know, right? Okay. All right, so let's talk about Maclaurin and Taylor series. Where are we? I posted these notes in that Zoom folder, in that folder that we have that I sent you the link for a few weeks ago. I put these in here last night. Make this a little bigger. So where we are now, okay, last section, what we saw was how we could take certain functions, right? They had to look a particular way. Can you all read that okay? Let me make that bigger for in here. I don't want to go too big or I won't be able. Is that okay for everyone here? All right, so we've seen how if you have a certain type of function, we can convert it to its power series using that geometric series thing from last time. And then we also looked at how you can look at a function and say, oh, that's the derivative of something, and then use that formula again, or it's the antiderivative of something. But in that section, we're very limited in actually what we can and cannot find this power series for. So today we're going to establish a general formula for finding the power series of just about everything, okay? Just about anything you ever want to do. This will be a general way of doing it. Now, something you might see in the future, we're going to get to that in just a second, but something that you might see in the future, maybe in an engineering class, physics class, you might see at some point that during the class, you might see that they'll take the sine function and they'll say, hey, the sine function is approximately x, as long as x is close to 0. Or you might even see them say, oh, cosine of x, it's approximately equal to 1 minus x squared over 2. And so like in some engineering class, maybe you're trying to do like, what is sine of 0.3? And instead of going and having to get a calculator out, you can just say, oh, well, that's approximately 0.3. That's this first one. Because 0.3 is close to 0, and this says it's about the same. And then here, if you wanted to say, okay, well, what's, cosine of 0.3, then that's approximately 1 minus 0.3 squared over 2. All right. Now, why is that true? We're gonna do that today. We're gonna show why those two are true, and why is it useful? Because you're taking a complicated trig function and converting it to basically a polynomial, right? That's what you're saying. You're approximating this sine function with a polynomial. Polynomials are just easier to work with. And then a cosine function, you're converting it over to a polynomial, right? It's a quadratic, right? So why are we allowed to do that? Okay, why can we do that? And I'll show you, okay? Let me clear this. I've forgotten how to use this thing. Oh, there we go. All right. So first, how do we find a formula, right? The whole idea here is that when you have a general power series, right? A general power series, this is what they all look like. That's the definition of a power series centered at A, right? You've got some numbers, these C sub n's, and then x minus a raised to the n. In every power series, this part here is always the same. It's always gonna be x minus a to the n, x minus a to, for all power series. The only thing that distinguishes power series from one another is the C sub n. That's really the thing that's different within each one. These constants in front are really what matters, okay? So can we find a formula for it? All right, can we find a formula for C sub n? Right, that's our task right now. Is there an easy way to find that formula? So let me see, I have the notes all typed up here, but I don't want to just go through the notes. I'm gonna go through this by hand. I think it's better to see it come to life rather than me do it all, just read this, right? So our task right now is to take a general power series. So we're assuming that some function can be written as the sum n equals 0 to infinity C sub n x minus a to the n. And then if we write the terms out, I am going to write these terms out. This would be C sub 0 and then x minus a to the what? To the 0, which would be a 1, right? And then we have plus C sub 1 and then x minus a to the first, and then C sub 2, x minus a to the second, C sub 3, x minus a to the third, C sub 4, x minus a to the fourth, plus dot, dot, dot. I might need more of these later, okay? That's all I can fit on that line. But just realize that it keeps going, right? So I want to try and see if I can find a formula for C sub n, right? Is there a way? So here's the way I'm going to do it. First thing I'm going to do is I'm going to try and figure out what C sub 0 is, right? Let's try and find C sub 0. So let's find C sub 0. So here's something very clever, all right? Here's something very clever. What I can do is I can take the original function and I can plug a in, all right? What happens if I plug a into this function? So if I plug in a, go into this and plug a in for x, and what happens? All these a minus a's become zeros. The only thing left is what? C sub 0, right? So here's what I'm saying. C sub 0 is just the function's value at a, all right? C sub 0 is the function's value at a. With me? Okay, now the next step, I need to try and find C sub 1. Now I can't do what I just did, because if I do what I just did, right, plug in a, I'm going to kill off everything. I'm just going to have C sub 0 again. So I'm going to do something really, really clever. This is not, of course, this is not my idea. This is what Taylor Maclaurin came up with, right? Or Taylor. All right. So these are mathematicians I'm talking about. So here's kind of the brilliant thing. Let's do this. Let's take the derivative of the function. Okay. And I'm not going to work with the power series. I'm going to work with the actual terms out here. It's easier to differentiate out here. So what would happen? Take derivative of the constant, it would go away, right? Okay, here, when I take the derivative, let's be careful. when you take derivative here, remember, this is really C sub 1x minus C times A, right? If I distribute the C sub 1 times A, right? I distribute through. If I do this, the derivative of this one would be what? C sub 1, right? And derivative of this would be 0, because both of those are constants, right? Y'all understand that? So this would be C sub 1 plus, now on this one, let's use the chain rule. The 2 would come out, right? Bring the 2 out front. So I get 2 C sub 2, and then x minus a to what power? First power, and then times the derivative of what's inside, which would be what? What's the derivative of what's in here?
1.
Just 1. Derivative of x is 1, derivative of a is 0. So you just have 1. So that's it, right? That's the derivative of the second piece. Let's keep going. Plus, now what would the next term be if I take derivative of C sub 3, x minus a to the third? 3 C sub 3, x minus a to the second. Okay, let's keep going. What would the next one be? 4 C sub 4, x minus a to the third. Let's keep going, even though I didn't write more terms. Let's do maybe one more. 5 C sub 5, x minus a to the fourth. You got the pattern? Can everyone see that? Keeps going. Okay, now plug a into the derivative, right? Take this derivative and plug a into it and tell me what you get. So doesn't it kill off all these terms down here? It kills off everything except C sub 1. And so now I know what C sub 1 is. C sub 1 is the derivative of the function at a. Okay, so C sub 0 was the function evaluated at a, right? C sub 1 was the derivative of the function evaluated at a. So you might be thinking, okay, well, maybe C sub 2 is the second derivative evaluated at a, right? And C sub 3 is the third derivative evaluated at a. It seems like maybe that's what's happening. Not quite. Let's keep going, all right? We will see a pattern, but let's, and I just want everyone to keep in mind right now, what we're doing is we're establishing a formula. Once we establish this formula, we'll never have to do this again. All right, this is just to establish the formula. All right, so now what do you think I should do if I'm trying to find C sub 2? Yeah, let's just do derivative again. Good. So we take derivative again, second derivative, and let's see what happens. We know the C sub 1, when we take derivative of that, it's going to go away. Now, when we take derivative of this one, this piece here, the 2 C sub 2 x minus a to the 1, I'm going to do it like a chain rule. I think it's a little easier to think of it as a chain rule. The 1 comes out, hits the 2 C sub 2, and then it'll be x minus a to the 0 power, which is a 1, and then the derivative of the inside, which is a 1 also. So all I'm getting basically is the 2 C sub 2, right? Another way you can look at it is this is a constant, comes for the ride, and the derivative of that is 1. However you want to look at it, we should get 2 C sub 2. And then now let's keep going. Plus, now when I do derivative of this one, what happens? The 2 pops out and you get a 6, right? Now I'm not going to write 6, okay? Because I know what's going to happen. I'm going to write 3 times 2. I'm going to leave it as 3 times 2, C sub 3, x minus a to the first, right? And then the next one, this 3 is going to pop out, right? And hit the 4. I'm not going to write 12. I'm going to write 4 times 3. C sub 4, x minus a squared. And then the next one, the 4 pops out. I'm going to write 5 times 4, C sub 5, x minus a to the third plus ... Okay? Questions on that? What do you think I do now? plug a in again, right, to the second derivative. So if we plug in a into this, we get just the 2c sub 2, right? Now solve that for c sub 2. How would I solve that for c sub 2? If I take that equation, solve it for c sub 2. Divide by 2, right? So you get f double prime of a divided by 2. Ah, shoot. So it doesn't follow, we thought maybe it would be, that c sub 0 was the function at a, c sub 1 was the first derivative at a, c sub 2 is not the second derivative at a, it's the second derivative at a divided by 2. Well, maybe maybe c sub 3 is the third derivative divided by 3? Maybe, I don't know. Let's see. Find c sub 3. So let's just keep doing this. Third derivative now. Now, when we start doing higher derivatives, instead of doing those prime marks, y'all know what we do? Instead of the primes, if I want to do the third derivative, you put a 3, but it has to be in parentheses. And that's because if you put just 3, people could think that you mean raise it to the third power. So the way we distinguish between a derivative and a power is to put a parenthesis around the 3. So that means the third derivative of this function. The 2c sub 2 is gone, right? It's a constant, it gets killed off. Now, on this first piece here, I'm going to have 3 times 2 c sub 3. That's what we get from the derivative of that term with x minus a to the first power. Now, what about this next term? 4 times 3 times 2. Ah, this is starting to look like what? Factorial. It's starting to look like a factorial. 4 times 3 times 2, c sub 4, x minus a to the first. And the next one will be 5 times 4 times 3, c sub 5, x minus a squared plus dot, dot, dot. Do y'all understand that? Just keeps on, you keep on popping these powers out. And so these coefficients in front keep growing, right? Okay, now, same procedure. Let's plug in a into the third derivative. Kills off everything. All we get is 3 times 2, c sub 3. Solve that for c sub 3, dividing both sides by 3 times 2. Anybody have a guess as to what c sub 4 is going to be? Anyone want to guess what it is? So at the fourth derivative of f, evaluated at a, over 4 times 3 times 2. Is that an approach? Do y'all see like that should be it? Do y'all believe that? Do I need to work through another one? You could just do the derivative again and see it, and then every time power's coming out. Now, could I then maybe come up with a general formula then? Oh, by the way, let's point something out here before I go any further. If you're guessing that this is actually correct, okay, this is the correct guess. Could I rewrite that as f, the fourth derivative at a over 4 factorial? Right? That's 4 times 3 times 2 times 1 is 4 factorial. There's a 1 next to this. And this one right here could be written as the third derivative at a over 3 times 2 times 1 is 3 factorial, right? Let's see if this pattern is working. This is the second derivative at a over, well, 2 is 2 factorial, right? And then this one right here, this would be the first derivative at a over 1 factorial, which is 1. And then if we go back one more, this is the 0th derivative, right? It's the 0th derivative at a. When you don't take the derivative, it's the original function over Well, 0 factorial, which is 1. So it works, right? Like this pattern, I think we've established. This is what Taylor was able to figure out. So here's our general formula. If we continue this down, then we would eventually get this. C sub n should be the nth derivative of the function at a over n factorial. And that is the big like, whoa, okay? Is we have a formula for finding the C sub n. So here's how this works. Somebody gives you a function, all right? And they say, hey, let's go find the power series for this. What you have to be able to do is take the derivatives. You have to be able to differentiate that function over and over and over and over, and then evaluate it at a single point. So this is always, I remember as a student, this confused me because it's like, wait a minute, you're trying to come up with a power series for a function, but to do that, you have to be able to take the derivative of the function. Like that seems odd. The way what we're doing here is we're saying this, we're trying to figure out what this function is everywhere, okay? Or at least within the interval of concordance, we're saying, can we find a way of representing this function? All we need in order to do it is you need to know at a single point, A, whatever A is, at that single point, you need to know the value of the function, the value of its first derivative, the value of the second derivative, the value of the third, fourth, fifth, sixth, seventh, eighth, ninth, forever. You have to know the value of the function at a single point, and from that, you can construct the entire function. Does that make sense? It's almost like energy. It's like not created nor destroyed, right? It's like we're not creating something from nothing. We're creating something from knowing a bunch of information about what's happening at a single point. Okay. All right. So let me get back to my notes. This is me in a nice clean way working through all of that again. So C sub 0 is f of a, C sub 1 is f prime, blah, 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 blah. Let's see how far I went. I went fourth. And then I actually made a table here to show like what's happening if n is 1. Oh, I forgot n is 0. Oops, I forgot to put n as 0 in my table. And then we get to our final formula here, n factorial, the nth derivative at a over n factorial. And I boxed it up. There it is. Okay. So let's get back to the Taylor, the power series, right? We started with this. And we said, hey, you know, is there any possible way that we can come up with a formula for that? And we just did. And since we now have a formula, what I can do is I can rewrite that power series again, replacing that, right? I have this, I replace the C sub n right there, and I replace it with my formula right there. That's it. It's a direct, just substitute that with the formula we just found. And I put it there. This is called a Taylor series of the function at A. That's what a Taylor series is. So look at, if we write this out, the first term of a Taylor series is the function's value at A. That's C sub 0. Plus, then the coefficient is the first derivative over 1 factorial, and then x minus a to the first power. Plus, the second derivative at a divided by 2 factorial, and then x minus a to the second power. And keep going and going and going and going. All right? That's a Taylor series centered at A. And A can be any number, right? A can be any number. The number that we use the most is 0. All right? That's the number we use most for Taylor series. So because we use it so much, we have a special name for that scenario. It's called the Maclaurin series. All right, so come on. If you take the previous result, okay, if you take the previous result and look when A is 0, which is the one we really like to use, then what happens? Replace all the A's here, everywhere here, with zeros, right? And what does the formula turn into? It turns into this. It's the nth derivative at 0 over n factorial, and then it's just x to the n because the a is 0, so it's just x to the n there. And then just rewrite everything. This is the Maclaurin series, and I just want you to know, just make sure you understand that a Maclaurin series is a Taylor series. It's just a Taylor series at a equals 0, all right? A Taylor series is not necessarily a Maclaurin series. It's kind of like this. A square can be considered a rectangle, but not every rectangle is a square. Make sense? It's the same sort of idea. Don't look at them as being completely different things. They are very much related. All right, y'all ready for your first example? Let's do it. This is gonna be fun. I've been looking forward to this all semester. We are gonna find the Taylor's, we're gonna start by doing a Maclaurin series. So there are the instructions. Find the Maclaurin series of f of x equals e to the x. So what does Maclaurin series tell us? Well, Maclaurin series tells us that a is 0. It's a Taylor with a is 0, right? So now what I need to know is this. Okay, I need to know the formula for that. I know that f of x must equal the sum n equals 0 to infinity of the nth derivative at 0 over n factorial x to the n. That's the formula I just had up on the board, right here. This right here. You need to know that formula to do a Maclaurin series. Okay, this highlighted right there in blue, that's the formula we just generated ourselves, okay? And then the x to the n is just the thing that we always have, the x minus a to the n. Okay, so that's what I need, right? That's what I need. So the way we do this, okay, the way we do this is we go see if we can find for our particular function, because now we actually have a specific function to look at. For our function, can we come up with a formula for the nth derivative at 0? That's what we need to try and find. A formula for the nth derivative at 0. If we can find it, we'll stick it right here, and then we will have our power series, our Maclaurin series. So the way I do this, or the way we are going to do this, remember the function is e to the x. We are going to take that function and just start taking derivatives of it. So I like to do this on the left side. I'm going to take the 0th derivative of the function. So the 0th derivative is just the function itself, isn't it? E to the x. Now let's take the first derivative. I'll use a prime mark. What's the derivative of e to the x? Itself, okay? And then let's do the second derivative, which is itself. This is boring. Let's do the third derivative, right? Itself again. And I could keep doing this, right? So if I go down to the nth derivative of the function, we're going to get e to the x, right? Now, we are not interested in the nth derivative at x, right? That's not what we want here. We want the nth derivative where? At 0, because it's Maclaurin series. So what I'm going to do now is to the right of this, I'm going to create another list that's going to be all of these derivatives evaluated at 0. So the 0th derivative at 0 is e to the 0. E to the 0 is what? 1. And that's going to happen for each of these, isn't it? F prime of 0 is e to the 0, which is 1. Every one of these is 1, right? Every one of these is 1. So the nth derivative, come on, man. The nth derivative at 0 is 1. That is a formula, isn't it? The nth derivative at 0 is 1, no matter what. This e to the x is like the most beautiful function because the c sub n formula is so simple. It's just 1, right? That's all it is 1. So I'm going to go back to this right here. And I'm going to replace the yellow with 1. One over n factorial x to the n. And that is the Maclaurin series for e to the x. Let's write out the terms of this. Let's start plugging in 0, then 1, then 2, then 3. Okay, I'm going to write it here. This is equal to, and let me put in front of this. We're saying here e to the x, which is the function we're looking at, is equal to this. E to the x is equal to, okay, start writing out the terms here. 1 over 0. I'm going to write them slowly here. 1 over 0 factorial x to the 0 plus 1 over 1 factorial x to the 1 plus 1 over 2 factorial x to the second plus 1 over 3 factorial x to the third plus 1 over 4 factorial x to the fourth plus ... forever. I'm going to rewrite it again. That first term, 1 over 0 factorial x to the 0, that's just a 1, right? And also the second term, I'm going to rewrite that as just x. The rest of them, I'm going to leave them alone. Look, everyone. We have a new definition for e to the x. This is what e to the x is. If you want to now try to figure out, well, you know what? Let's look at the second example. We're done. That's the Maclaurin series. By the way, and I'm not going to do this in class. If this is the power series for e to the x, couldn't I ask you to find the radius of convergence? And you would run a ratio test on that, wouldn't you? You would take this thing in here and run a ratio test. If you do that, the radius of convergence will be infinity, which means it converges on the entire number line, all right, everywhere. I'm not going to ask you to do that. Just understand that you could, right? So, two things before we move on. First thing is in your formula sheets, there's a thing called Maclaurin, and it's a list of functions, common functions that we see, and their Maclaurin series. And you'll see this. The first one here is the geometric series that we studied last class. This is from 8.6. We could rewrite 1 over 1 minus x as the sum n equals 0 to infinity of x to the n, which is this, but it has a radius of convergence of 1 because the absolute value of x had to be absolute value of x had to be less than 1. So it was good, but only within a certain window. The second function, e to the x, we just found its power series. They put the n factorial under the x to the n. We put 1 over n factorial x to the n. They just slid it underneath. It's this. And look, they're telling you in this that the radius convergence is infinite. All right. So that's the first thing I wanted to point out is that this table you can have on your test, your final. There will be problems on the test where I will tell you you can use that table, and there are problems where you're not allowed to use the table. All right. And I'll be specific when I'm testing you. The other thing that I want to show you is here. I want to show you that what we just did actually works and makes sense. I don't. Okay, I'm going to have to go real quick into the code here. A couple of things I forgot to do. Get rid of this. Okay, there we go. So the red function is e to the x. What the hell? I forgot to change that yesterday. There we go. The red function is e to the x, the good old e to the x that we know. And then the black is our Maclaurin series. What's the first term of our Maclaurin series? Nope. What's the first term? Look at it. 1, right? So right now I'm graphing the constant 1 function. It's not a very good approximation to e to the x, right? But now as I add more things, what's the next term? X. So 1 plus x, let me graph that. That should be a line, shouldn't it? 1 plus x, that's the line. It's an approximation of e to the x, not very good. Now 1 plus x squared over 2. Look at what happens. There it is. There's the black one. It's better, right? Let's keep going. Better. Just keep, now watch the black one. Watch it start to like kind of merge itself into e to the x. It's becoming e to the x. It is e to the x. if we could go out forever, it's e to the x. All right. Pretty awesome. Radius of convergence being infinite means that we can use the Maclaurin series and it's accurate anywhere. We can go anywhere. If I wanted to look at the function way down the number line somewhere, I can still use this Maclaurin series. Whereas when you're using that 1 over 1 minus x, because you have a radius convergence of 1, we might have to slide it around, move it around. Okay. This is great. This is outstanding. And the last thing is look at this beautiful, beautiful thing. What is the derivative? What is the derivative of e to the x supposed to be? Itself, right? Well, let's check, right? Let's take the derivative of the power series. What's derivative 1? What's derivative x? 1, okay, plus. Now, this is 2 factorial, right? So do power rule. 2 comes out, cancels out with 2 factorial is 2, isn't it? So it cancels out and you just get x. Plus, now check this one out. The 3 comes out. Think about that 3 coming out, right? 3 comes out. On the bottom, you have 3 factorial, which is 3 times 2. And then the x power becomes 2 now, right? The 3's cancel, and you just get 1 over 2 x squared, right? Which is 2 factorial. Now do the next one, which is this one. The 4 comes out. It's over 4 factorial, right? X to the 3rd. The 4's cancel, but you still have 3 factorial down there. So this is 1 over 3 factorial, x to the 3rd. And if we keep doing this, look at it. I mean, it matches. It's the same damn function. Okay? That's beautiful. I mean, it's the only function out there in the world that does that. There's no other function that does that. This is the only one. All right. Pretty cool, huh? All right, so what's in a box here is the thing you really need to know, all right? We back this out. You ready for the next example?
You're on a test, would you want us to write it out right now, or put it in sigma?
So the question is, on a test, would I want the series, if I ask you to find the Maclaurin series for something, do I want the sigma notation, or do I want the terms written out? I don't care. But you should, I think it's always good to just write out a few of the terms anyway. You know, I won't care if your series is right, or if you just write the terms, it's okay. Here, you know, there's another way I could have done this. Well, you know what, maybe I'll do it on this next one. Yeah, let me try it on the next one, maybe. Next example. This was, sorry, I forgot, I wanted to do this. Use your example from, use your answer from example 1 to find a new expression for E. Just E itself. Not e to the x, just E. So what's another way we can, because you know how we've had trouble in the past defining like what is E? Like, right? We've been like, what's E? What's E? Well, we have now, we have a way of defining it. Watch. Let me go grab what we just did, this piece right here. That's what e to the x is, right? All right, that's e to the x. So e is just e to what power?
1.
E to the 1, right? So just plug in 1 for x. 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial. See, all the x's are 1s now. So 1 to any power is just 1. So this is it. And if you don't believe it, just get on your calculator and do 1 plus 1 plus 1 over 2 plus 1 over 3 factorial is 6. So 1 over 6 plus 1 over 4 factorial is 24. So 1 over 24. If you start typing that in, you're going to get a number that's going to get closer and closer to 2.718, blah, blah, blah. That is E. And if you want to get more decimals, you go further and further out into the series. Same with E squared. And this is what I was saying. When you type in E, right, on your calculator, when you type in E cubed, your calculator is just using this series. That's all it's doing. It's using that. That's pre-programmed into the memory of with the, you know, someone programmed the calculator, right? So that's predetermined. It's a predetermined formula. All right, now the next example. How are we doing on time? Find the Taylor series for e to the x at a equals 2. So we just did the Maclaurin series for e to the x, right? Now we're going to do the Taylor series at a equals 2. All that changes here, all that changes is the formula we're going to use. We're going to use the Taylor formula, which is sum n equals 0 to infinity. The nth derivative where? At two, I'm going to do the general formula first. At a, right, over n factorial x minus a to the n. That's Taylor, right? Maclaurin is Taylor with a being 0. Taylor itself is a. And we want to take that formula and we want to replace the a's with 2 here. My stomach is growling and I just realized I made myself some breakfast and I forgot to eat it. Okay. So all I did there is replace the a's with 2. And again, I'm going to go after this. I'm going to see, can I look at what the nth derivative of the function is at 2 instead of at what? It was 0 before, right? So I'm going to do this the same way. I'm going to start taking derivatives. The 0th derivative of this function, well, what is it? What is the original function? E to the x. So it's e to the x. And we already know what's going to happen here, right? All of these are going to be e to the x the whole way down. So even when we get to the nth derivative, we're going to have e to the x. But now instead of plugging in 0, I'm going to plug in 2, right? Plug in 2. So the 0th derivative at 2 gives me what? E squared, right? And each one of these are going to be e squared all the way down to the bottom, e squared. That's what the nth derivative at 2 is. And again, this is a nice formula. It's a constant again, isn't it? What was it from Maclaurin? What did we get there at the end from Maclaurin? We got a 1, right? Here we got e squared. Okay. So I'm just going to take this now. No, not that one. Take this one and I'm ready to write it out. I'm going to bring it down a little bit further. Okay, this should be the sum n equals 0 to infinity. Okay, the nth derivative at 2, we just said that that's e squared over n factorial, then x minus 2 to the n. There it is. That is the Taylor series for e to the x centered at a equals 2, or centered at 2. Now, just to say this, we would never need to do this, like center it anywhere other than 0, because I already said the radius of convergence is everything. So there's no need to move it. But this is just a first example. Let's write out just a few of the first terms. If I plug in 0, I get e squared over 0 factorial, and then x minus 2 to the 0, plus e squared over 1 factorial, x minus 2 to the first, plus e squared over 2 factorial, x minus 2 squared, one more, e squared over 3 factorial, x minus 2 to the third, plus ... All right, we're done. Questions, concerns, complaints? Next example. Can't believe we're halfway through class. Example 4. Here we go. Find the Maclaurin series for sine. Okay, now we want to do Maclaurin series, right? So that means it's centered, it's a Taylor centered at 0. So the formula I'm going to be using here is sum n equals 0 to infinity of the nth derivative at 0 over n factorial x to the n. All right, I would like to, I'm going to do this slightly different. There will be enough similarities that you'll see, but sometimes the method that I'm doing now will be a little bit easier. Here's what I'm going to do. I'm going to start writing this out generally. So if I do this, it's the first term is the 0th derivative at 0 over 0 factorial x to the 0. Then the first derivative at 0 over 1 factorial x to the first power. Then the second derivative at 0 over 2 factorial x squared. Then the third derivative at 0 over 3 factorial x to the third plus ... I'm just writing them out. Now I'm going to go get that formula. Okay, I'm going to go get that formula. The nth derivative, I need the nth derivative of this function at 0. Here we go. Feel good? All right. For the nth derivative is the 0th derivative of this function is just the function itself, which is sine x. Then we take the first derivative. The first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. What's the fourth derivative? Back to sine x, right? We're back to sine x. And now it's just going to continue this pattern, right? It's going to go cosine, negative cosine, then back to sine. It's cyclical. That's a cyclical, we call it cyclical because it's going through some cycle. I'll do maybe one more here. Fifth derivative. Okay, fine. Let's see. Do we have, what I need to ask you here is, do we have a general way of writing the nth derivative? This is harder to do. Do y'all see this is harder to do than e to the x? Okay, the nth derivative here at x, do we know what it is? Well, wouldn't it depend on n, right? So like if n was 0, or if n was 4, or if n was what, 0, 4, or 8, or 12, then it would be sine, wouldn't it? And if it's 1 or what, 5, 1 or 5, or what would come next? 9 or 13, then it would be cosine, right? And then if it's, I'm running out of colors here. If it's 2, or what would be the next one? 6, then it would be something else. So I don't have an easy way of writing the formula. Do y'all agree with that? There's not an easy way to write it. But I know there's a pattern. Understand? So instead of me trying to find this, I'm just going to go plug in the numbers. But plug in 0 into these and see if there's a pattern here that I can establish. So if we do the 0th derivative, but now plug 0 in, right? Because it's Maclaurin. Sine of 0 is 0. And then we do the first derivative at 0, which is cosine of 0, which is 1. And then we do the second derivative at 0, which is negative sine of 0, which is negative 0, which is 0, right? And then the third derivative at 0. Why am I plugging in 0? Why am I plugging in 0? It's Maclaurin, right? It's Maclaurin, right? That's why I want to make sure everyone understands why 0 is going in here. It's Maclaurin. -1. And then what's going to happen? It's going to continue the pattern. It's going to go back to 0, then 1, then 0, then -1, then 0, then 1, then 0, then -1, right? Isn't that the pattern? But again, you don't have a general pattern at the end. Do y'all see that? Like, I can't tell you what the nth, I can't tell you easily, okay? I can't tell you easily what the nth derivative is at 0 is, because it will depend on what n is. There's 4 different scenarios, right? There's 4 different scenarios. And that sucks. We cannot come up with a general formula. Do y'all understand that? Not easily. But even though we can't do this easily, we can start writing them out. We can start writing them out because I know what each of these top pieces are, don't I? I know what each of those numerators are. Those are these numbers right here, right? That's this one, and this one, and this one. Do y'all see that? So I'm going to start doing that, and I need space. I'm going to see if I can move this whole, yeah, I'm going to cheat. I'm going to move the whole thing down so I have some space above it. I'm going to start writing this right here out. Everything here, I'm going to start writing it out above it. So this right here should equal, okay, what was the 0th derivative at 0? It was 0. So that whole first term is gone, right? Everything here is gone. Plus, now what was the first derivative at 0? It was 1. So I'm going to have 1 over 1 factorial x to the first power. Now, what about the 2? Gone, right? The second derivative at 0 was 0. So that's going to be nothing. Then plus, what about the third derivative at 0? It was -1, right? Over 3 factorial. X to the third. We should be able to establish the pattern now. All the even powers are gone, aren't they? Because on every even I get zeros. Now the odds are going to be either 1 or -1, and they're going to keep alternating, aren't they? Alternating? Did I just say that? Okay, so what would my next term be? Can someone tell me what it would be? You want me to include the zeros? I will. 0, that's the fourth one, the fourth derivative. And then plus, what would the next one be?
-1/5 factorial.
Is it negative? What would the fifth? Yeah, be careful. What would the fifth derivative, right, would be cosine. Cosine of 0 would give us the 1. We would be back to a +1. Jair, you got that?
Yes.
Okay. X to the 5th, then a 0 for the 6th power. Now you would get your what? -1. That would be the 7th derivative, which is not on my list. But again, we're trying to find this pattern that it goes 0, 1, 0, -1, 0, 1, 0, -1, 0, 1, 0, -1. So we should have -1 over 7 factorial, x to the 7th. And then that keeps going, right? I'm going to condense this down. Sorry, I'm going to move up again. Let's get rid of all the zeros. This is going to be, how do we want to write? Yeah, let's just write this as, yeah, I'm going to do 1 over 1 factorial x to the first power. Then I'm going to write minus 1 over 3 factorial x to the third power. Then plus 1 over 5 factorial x to the 5th power. Then minus 1 over 7 factorial x to the 7th power. Plus, I know the next one, right? It's going to be another odd. It's going to be a positive 1 over 9 factorial x to the 9th. What would the next one be? Minus 1 over 11 factorial x to the 11th. And then I could keep going, right? Understand? This is the Maclaurin series, all right? Let's see now, can we get this into a sigma notation? And this goes back to almost like the stuff we were doing back in 8.1. Do y'all see that this series alternates? I'm going to start it at 0. Let's start it at 0 because it's a power series. Okay, it starts at 0. Let's look at the alternating. It starts positive then negative, positive then negative. So how can I do that? -1 to the n power, because we're starting at 0. That should take care of the alternating. Let's look at all of the powers of the x's. They're all odds, right? So we want to all the odds starting at 1. So yeah, no, you're right. You're right. All the odds starting at 1. So let's put x to the 2n plus 1. Right now, this, if I start plugging 0 in here, I'll start with 1. And then after that, I'll get 3 and then 5, then 7. Make sense? But all the denominators are these factorials. These factorials are all the odds, right? Odd factorials starting with 1 factorial. So on the bottom, I need what? 2n plus 1 in parentheses factorial. And we have just created the Maclaurin series for sine. Questions?
Sir, I have a question.
Yes.
Can you go down a bit?
Yeah.
For the nth derivative of x, couldn't you make that sine of x plus pi over 2n? Maybe.
There might be a way that we can come up with a formula for this, but
Yeah.
this is an illustration of where, like in the previous example with e to the x, easy to take the derivatives. They're all the same. So there's an easy formula. Here, easy to figure out the pattern here. It's always 1. We're in business. Like there's no problems. This is the way we want to do it. We want to just replace that formula with 1 and we're good. But this is their first example where, you know what? If this becomes a tedious pain, forget the formula, establish the pattern, write out the terms. Once you have the terms, then you create the formula.
Yeah, it's easier that way.
Pardon me?
It's easier that way.
Yes, definitely easier this way. Absolutely. Absolutely. I still think even if you found some formula here, you would still have some trouble here. But that, if you want, we can talk about that more outside of class. Maybe there is a way to get something there. All right, a couple of things I want to point out about this formula we just found. And I believe I mentioned this to you when we first started talking about this stuff. Here it is on the sheet, right? This is the formula we just came up with. All the powers of this function, right? All the powers are odd. And that's why we said in pre-cal that sine was an odd function. It's because its power series, its Maclaurin series contains only odd powers. And you also learn in college algebra that the cosine function is an even function. And you can tell by its Maclaurin series that the powers are even. That is why, in college algebra, you're taught what even and odd means, but that's actually not the definition. The definition of even and odd has to do with its Maclaurin series. It's whether or not the powers are even or odd. Reflections, yeah, symmetry, which is true. It does have that symmetric property, but why call it odd? Like you could call it symmetric, or you call it, why call it odd and even? It's because of this. That's where that's why we're picking up the odd and even in the language. And e to the x is neither, right? And the reason it's neither is because it evens and odds. Okay, pretty cool. All right, what do you think's coming next? Cosine. Let's do cosine. It wouldn't be a true Cal 2 class if we didn't do cosine. You want me to let you try? You think you can create the cosine on your own yet or no? Why don't you do this? Take the cosine function, create a list of its derivatives, and then plug 0 into each of those, and then see from there if you can, at least start with that. It's going to be very similar to the one we just did. Oh, hey, I forgot to show you before we get too far. Hold on. I forgot to actually show you that this works. The radius is infinity for sine. Yeah, it's everything. It's actually really cool that it works that way. So our Maclaurin series, here's the sine function. I think this is just beautiful when you watch this. What's the first term of our series for our Maclaurin for sine? X? X. Wait a minute, hold on. Isn't that? I've got so much damn information here. I'm all over the place. Hold on. Remember in the beginning of the notes today, I said something you might see in the future. I said sine of X is approximately X when X is close to 0. Why is it X? Because that's the first term of our Maclaurin series. And then this is going to be the first 2 terms of the cosine Maclaurin series. So if you wanted even more accuracy, you could include with this minus x cubed over 6. That would be the second term of the Maclaurin series. But in most physics classes, this is good enough. In fact, how good? I did something last night to show how good. Let me see if I actually brought it here. God, I wish we had more time. I was messing with this last night. Let's see if I put it in here. Where did I put? Oh, no, I put it in the other folder because I want to use it later. I was thinking, how close is sine X to X? Like, how close really is it? All right, that's what I was thinking. Come on, man, get over here. Shit. Oh my God, this little toolbar just totally messes me up with Zoom. Oh, damn it. Can't move this thing. Here we go. Doesn't want to move. There it is. Shit. Oh, now I lost all my windows. Okay, so I know this is hard to see, but so what I want you to look at here, because there's a lot of shit going on here. What I want you to see here is this column right here is the angle in radians. And so I start with 10 radians and I start going down and getting closer and closer and closer to 0, okay? And then this is just the angle in degrees, okay? So this is the angle in radians, and then right here, this is the sine of the angle. So you can see this is like X and this is sine of X. So if I plug in 10, sine of 10 is really not close to 10 at all, right? These are not very close to one another. The difference between the two is 10. But as I start letting the angle get closer to 0, watch what's happening here. These are starting to get closer to one another. And this is me calculating the difference between the two. So look at this. When you put in 0.8 into the sine function, it spits out 0.7, right? That's pretty close to one another. If you plug in 0.5, it's 0.47, 0.4, it's 0.38, 0.3, it's 0.29. Right when you get to about here, man, they're almost the same. And if you round it up, right? In fact, and look at this, this is at 17 degrees. So when your angle is 17 degrees, the difference between using sine X and X itself is essentially, they're the same from 17 degrees down. And so, you know, look at my angles here. If I go to something like 4 degrees, which is 0.07 radians, sine, and these are like almost the same number. They're off by 0.00057. Very similar to one another. And then, yeah, the more you go, that's why in an engineering class, you approximate sine of X with X as long as the angle's small. Okay, I lost so many windows here. What was I doing? What were you doing? You were going to try this cosine one, right? I was going to. Oh, yeah. Thank you. I think I would have got to it right here. Okay, here we go. So there's X, right? There's X, not a very good approximation. Minus X cubed over 6, which is 3 factorial. So just see it starting to build up here. It's just, this is just freaking incredible. This has always blown my mind that you can create a polynomial function that just starts like just melting its way onto the sine function. And the further you go, the better it gets. And it just the more terms you add, it just starts building out the sine function. It's just awesome.
In the real world, you'd only use like the first part, right? So
Yeah, in the real world, you know, you have to determine how many of these terms you actually need. You don't need all this because, you know, in the beginning here, like in the middle at 0, man, this is like basically, it is like essentially the same function. It's not, it's going to be off a little bit, but it's going to be off like to hundreds of decimal places. You know, you have to go out before there's a difference. It doesn't matter because I think I said before, when it comes to, there's a difference between theoretical and application, right? If you're building a ball bearing for an aircraft, like you can only build it within a certain precision anyway, right? Yeah, the tolerances, you know, I mean, so if you need me to be real accurate, I'll just get more terms. That's you know, fine. I'm never going to run out of terms. You'll run out of ability to make it that way. Okay, now you're doing cosine. Y'all are probably done by now. Yeah, it's just shifted over. So this should be the same thing we had before. The nth derivative at 0 over n factorial x to the n. This should be equal to the 0th derivative at 0 over 0 factorial plus the first derivative at 0 over 1 factorial plus the second derivative at 0 over 2 factorial, x to the, I forgot my x's. Y'all take the derivatives. Oh man. X. I have a better idea. I'm just gonna go steal it from the other one. Yeah, just move them.
Just forget the top one.
Yeah, I could do that. Let me see. Okay, so that's our general formula here for the Maclaurin. And then my table of derivatives. 0th derivative of x is the original function cosine. And now I'm just going to list them out. I'm not going to write, I'll write one more of these and that's it. First derivative would be negative sine, then cosine, then, wait, hold on. Cosine, derivative sine is negative cosine and then sine and then cosine. So we're back to, we complete the cycle here. So now it just continues to repeat. Y'all okay at home? We're having fun in here. Are y'all all right?
Yeah.
Okay. Plug 0 into each of these. You plug in 0 into the 0th derivative or the first derivative. We should get what? What are the list of numbers here? 1, 0, -1, 0, then 1, then 0, then -1, then 0, then 1. So it's the same sort of pattern that we had before, but it's offset a little bit. And that's why we're going to kill all the odds are going to get killed and all the evens get picked up and they alternate. Yeah. Mm-hmm. Yeah, tangent's different, right? Yeah, we're not ready for tangent yet, but yeah, tangent's a little bit tricky. All right. So now I'm going to go back up here and cheat. I'm not going to try and come up with a formula. I'm just going to plug into this. So all the odds are gone, right? All the odds are gone. So I'm not even going to look at the odds. I'm just going to look at the evens. So I have a 1 over 0 factorial x to the 0. And then the next one should be the even one. So that was a 1. I get a 0 kill off. Then the 1 will go onto this one. So sorry, -1 will go into that one over 2 factorial x squared. The odd one's gone. The next even one should have a positive 1 on top over 4 factorial x to the 4th. Then I'll get a -1 on top over 6 factorial x to the 6th, and so on and so forth. Questions on that? Y'all understand? Everyone here, I think in class feels okay with this. Are y'all at home doing all right with it?
Yeah.
Any questions? We need to create the formula. So it needs to alternate and it needs to start positive again. So -1 to the n. Okay, all the powers on the x's are even powers starting with 0. So I will want to use 2n. And then that'll be over all the factorials on the bottom are even starting with 0 factorial. So I'll put 2n in parentheses here, factorial. And that is your Maclaurin series for cosine. Okay. That's your Maclaurin series for cosine. I'm going to write it out a little bit better. It would be 1, because all of this right here is just x is 0, and that's a 1. That's 1. Then minus 1 over 2 factorial x squared. Then plus 1 over 4 factorial x to the 4th. Then minus 1 over 6 factorial x to the 6th plus ... That's it. Good. I'm going to show y'all something really cool. Ready? Watch this. This is cool. Where was our answer for this one? This was sine, right? This was sine. This is sine x. What's the derivative of sine? Watch. Take the derivative of this. Okay, that's really just x, right? What's the derivative of that? 1. Okay, now, when you bring this 3 out, it cancels with one of the 3's from the factorial, which leaves you with a 2 down there, right? So you have minus 1 over 2 factorial x squared. Now the next one, bring the 5 down. The 5 cancels, but you still have 4 times 3 times 2. That's 1 over 4 factorial x to the 4th. I mean, this should be pretty freaking awesome in your minds, right? What is that? I mean, that is the formula we just got for cosine, right? That's cosine. So just like I showed, derivative e to the x was itself when you did the series and you took its derivative, it was itself. When you take derivative of sine, series, Maclaurin series, you get the cosine Maclaurin series. So in theory, you could create the Maclaurin for cosine by just knowing the sine Maclaurin and just differentiate it. Yeah. Okay. Yeah, pretty freaking awesome. Think about this. Nah, we won't think about that. I'm going to go way too far off on a tangent. I'm sorry. I don't want to go way off here. We're ready. Okay, this one, let me just read about that. This is just to show you again. This is us approximating the cosine function with 1. That's the first term. There's 1 minus x squared. That's right there. That right there is why I said in the beginning in a engineering class, physics class, you approximate cosine x with 1 minus x squared over 2. You need the second term, right? The first term, this is just way too, this is not good. Okay. So you need that, you know? And then you just keep going and it builds it up and it's all good. All right. Okay, so I need to concede that there's no way I'm getting through today's material with 20 minutes left. So with that in mind, I need to decide what I want to do next. Sine, cosine. Yeah, we can do this one. It's super fast. Yeah, we can do this. This is super fast. So look, now what I'm asking for is find the Maclaurin series of x squared cosine x, right? Well, we already just did this Maclaurin for cosine, didn't we? So if I want to do this, I'm going to do x squared times cosine x. That's the function we're trying to find the Maclaurin series for, but that's x squared times the sum, n equals 0 to infinity, -1 to the n, x to the 2n over 2n factorial. That's the Maclaurin for cosine, right? So this index here, n, right? N is what's being affected here. X isn't, right? So I can multiply this x in here. I can put it in. And when I put it in, I multiply here x squared, get rid of it out here. And now I have x to the 2n times x squared, just add the exponents. And now I have a new power series. Yeah, we couldn't, yeah, that would, yeah, but that would never be x to the n. It would always have to be a fixed number if you want to actually talk about it as a function, right? X to the third or x to the fifth or, right? Yeah, this is much easier, right? So this x to the 2n plus 2 over 2n factorial. And then we could start writing out the terms, right? Like let's plug in 0. When you plug in 0, this time you don't get 1, you get what? You get, when you plug in 0, this becomes x squared, doesn't it? And then everything else stays, so x squared, right? And then, and so look, just take the Maclaurin series for cosine, which was this, right? This was Maclaurin for cosine, wasn't it? I could have done this problem this way. I could have said instead of this, I could have gone from here. I could have said, well, this is the same as taking this and multiplying by x squared and just distribute it. Yeah, you do that too. This shows both ways. This shows how you can distribute it through the Maclaurin, or you can, do that, rewrite the sum. Now, look at how freaking awesome this is now. Watch. Let's say I wanted to know the antiderivative of x squared cosine x dx. If I ask you to do that right now, you're going to start cranking out integration by parts. You're going to have to do integration by parts twice, right? That's what you're going to have to do. But this is the same as integrating the infinite series. Now, I haven't distributed this through, right? But it would be x squared would be the first term minus what, 1/2 x to the 4th. And the next term would be 4 factorial is 24. So it'd be plus 1 over 24 x to the 6th, right? Because I have to distribute that x squared through. And then whatever the next one is, minus 1 over 6 factorial. I think that's 120. 6 factorial, I think is 120. Someone can confirm. 120 x to the what? 8th plus ... right? dx. And then just power rule. No integration by parts, right? 1/3 x cubed minus 1 over 2 times 5 x to the 5th plus 1 over 24 times 7 x to the 7th, right? And then you're like, well, wait a minute, I can't go forever, right? And then we have that argument again. Well, shit, how accurate do you need to be? You know, I mean, you want me to go further, I'll go further, right? But I'd rather do that than to do integration by parts. And then, yeah, so what about this? What if I change this problem to x to the 20th cosine x, right? Like you definitely don't want to do integration by parts now. Like I think you don't want to do it 20 times, but it'd be easy to pass an x to the 20th through this, right? Power series are just so much easier to work with, right? So much easier. All right. I'm going to skip binomial for now because I don't have time. God, I really want to show you all the most beautiful formula in math. I do have 15 minutes. So I've worked it all out here already for you. Okay, but I'm not going to go through that. If you want to go back and look in the notes, it'll be here. So we talked last time at the end of class about how mathematicians argue that this formula is the most beautiful equation in math, right? Beauty is subjective though, right? We know that. So it's obviously, it's not agreed upon, right? That this is the most beautiful formula in math. But a lot of people do look at it that way. So most people that I know that think that this is the most beautiful formula in math is because they've been told it's the most beautiful formula in math. It's not because that's their opinion. All right. And I talked last time about why it's nice. It's got 0, it's got 1, it's got e, it's got I, it's got pi. So to show you that this is true, let me just make sure you agree with this. All I have to show you is this. If I can show you this, you will be satisfied. I'm going to try and show you. I want to show that e to the I pi equals -1. Would you be convinced if I could just prove that to you? Yeah, just move the 1 to the other side, and that would be what I'm going to try and show. That's what I'm going to try and show. Before I actually do it, though, I need to establish something, some properties of I. So I, by definition, is the square root of -1. It's this imaginary number that we don't spend any time on, all right? And so if I take the property of I is that if you square it, you get rid of the square root and you get -1, right? Now I'm going to keep going. I'm going to cube it now. If I cube it, that would be I squared times I, wouldn't it? Which would be, well, I squared was what? -1. So that's just -1 times I, and that's just -I, right? I'm going to leave it as -I. Okay, keep going. I to the 4th. Wouldn't that be I squared times I squared? Which is -1 times -1, which is +1. Yeah? How about I to the 5th? Well, wouldn't that be I to the 4th times I? But that's just, I to the 4th we just said was 1, right? So that's 1 times I, so that's just I. So I'm back to where I started, aren't I? So look, I to the 1st power was I squared was -1, I cubed was -I, and then I to the 4th was +1, and then I to the 5th was back to I. And now as I continue, this is going to continue. I'm going to just write it because I'm going to need it. I to the 6th would be -1, I to the 7th would be I to the 8th, 1, and then I to the 9th would be back to I, right? I is cyclical. It's cyclical also. It goes, now it's 4 cycles, right? It's I -1, -I, 1. I -1, -I, 1. That's what it keeps doing. With me? Okay, here we go. That's all we need. That's all we need. So the first problem we did in class today was this, right? Right here. We found the power series, Maclaurin series for e to the x, right? I'm going to use that. So remember that e to the x is equal to sum n equals 0 to infinity of 1 over n factorial x to the n, which is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the 4th plus dot, 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 dot. It keeps going, right? What I'm going to do is instead of plugging in x, I'm going to plug in I pi. I'm sorry, no, ix. Let me do ix. Okay, so remember what I said I wanted to show. E to the I pi was equal to -1 is what I want to show you, right? I'm going to plug in e to the ix into this. Replace x with ix, and this formula becomes, let's not look at this. Let's just plug it in here. I would have 1 plus what? Replace the x with ix. So 1 plus ix, okay, plus 1 over 2 factorial, what? What? Ix squared. Okay, plus 1 over 3 factorial ix cubed. Plus, I need a lot of these. 1 over 4 factorial ix to the 4th, plus 1 over 5 factorial ix to the 5th, plus 1 over 6 factorial ix to the 6th. I'll try and get one more in here. 1 over 7 factorial ix to the 7, plus dot, 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 keeps going, right? All right, now, I'm going to actually square, cube, and 4th power all those things. So this becomes 1 plus ix plus 1 over 2 factorial I squared times x squared, right? Plus 1 over 3 factorial I cubed x cubed plus 1 over 4 factorial I to the 4th x to the 4th. With me? I'm just getting rid of the parentheses. Plus 1 over 5 factorial I to the 5th x to the 5th. 1 over 6 factorial I to the 6th x to the 6th. 1 over 7 factorial I to the 7th x to the 7th plus dot, dot, dot. Okay, now we keep going using what I just said here. If I have I to the 1st power, 5th power, 9th power, those are all just going to be i's. If I have 2nd power, 6th power, what, 10th power, that would be -1. If I have 3rd power, 7th power, or 11th power, it'll be -i. And if I have 4th power or 8th power, it's going to be 1. Okay, let's do that. This is going to be 1 plus ix. Okay, what does the I squared become? -1. So I'm going to put this as -1 over 2 factorial, 1 over 2 factorial x squared. That's what that becomes, right? The I squared becomes a -1. Okay, next one is, let's see, I cubed is what? -i, right? So now this is going to become, because I cubed is a -i, I'm going to put the negative in front, 1 over 3 factorial I, right? We still have an I there. I cubed became -i. So I changed this to a minus and then an I. Yes? The next one is a 1. So this becomes plus 1 over 4 factorial, just x to the 4th. What about I to the 5th? I to the 5th was just I, right? So I to the 5th, this just becomes plus 1 over 5 factorial I x to the 5th. I to the 6th, what's I to the 6th? -1, right? So this becomes a -1 over 6 factorial x to the 6th. How about I to the 7th? -i. So this is going to become -1 over 7 factorial I x to the 7th. What would the next one be? 8. The 8th one here. The 8th one would have been a 1, right? I'm going to just put that 1, and it would have been plus 1 over 8 factorial x to the 8th, right? I'm going to stop there, plus dot, 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 dot. Whoa, what a mess, right? What a mess. Okay, check this shit out. This is so cool. Watch. Everything that has an I in it, I'm going to separate and move to the side. Everything else doesn't have an I in it, right? So I'm just going to rewrite it. First, let me write the stuff without the I's. 1 plus, or sorry, 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial 4x to the 4th minus 1 over 6 factorial x to the 6th plus 1 over 8 factorial x. That look familiar, right? Okay, plus, now that keeps going, right? That keeps going with all the stuff without i's. Then I have all the stuff with i's. Okay, so now when I write everything that's in blue, everything in blue has an I in it, right? So I'm going to factor an I out. I'm going to pull an I out. And now tell me what the blue parts would be without the I, without the i's. X minus 1/3, 1 over 3 factorial x to the 3rd plus 1 over 5 factorial x to the 5th minus, that look familiar? 1 over 7 factorial x to the 7th plus dot, dot, dot. Now we keep going, right? So what is this? What is that?
Cosine.
What is that? That's just cosine x, right? This is just cosine x plus I times all of that is sine of x. This is what e to the I x is defined to be, right? E to the I x is cosine of x plus I times sine of x. Plug in pi for x. E to the I pi would then be cosine of pi plus I times sine of pi. And sine of pi is 0. And cosine of pi is -1. And then it's shown. It's proven. It's pretty cool, right? So Euler came up with this brilliant, historically way up on the totem pole of mathematicians. He came up with this. This is for those of you who do, more physics stuff, engineering, there's a famous formula that involves this e to the I. I do have 3 minutes. We're pretty much done with this. We still have more to do in this section. So what I'd recommend is on the homework, just, start trying to do problems. Make sure you've got all the other homework done. There's a very, very famous, from this, we can deduce this. All complex numbers, right? I know you've done just very little with complex numbers. A complex number is a number that lives in two-dimensional space where it has like an x coordinate and a y coordinate. The x coordinate is what's called the real part, and then the y coordinate is called the imaginary part. You may have looked at this in college algebra and may not. I know I don't go into detail. What this formula allows us to do is say that every number in every complex number, instead of looking at it like that, you can look at the distance from here to here, call it r, and the angle from here to here, call it theta, and then use this formula, r e to the I theta, and that will give you this number, this complex number. For example, if you want to take the number 3, okay, and you want to write it, what you can do is just tell me what the angle is to get to 3. What's the angle? What angle gets you out to 3? 0. Okay, so replace the theta with 0. And then what's the radius? How far out is it? 3. Put that for r. And now just do that. What's e to the 0? E to 0 is 1. So this is just 3, right? So of course that's the number 3. Now, what number is right in the complex numbers right here? What is that number? Just go up 1. This is called the imaginary axis. This is the number I in the imaginary numbers. Okay, it's just, you basically rotate by how much? 90, so that's e to the I times pi over 2. And then what's the radius to go up 1? 1, right? So this is actually another definition of what I is. That's what I is. I is e to the I times pi over 2. I know this is complicated looking, but think about it this way now. What's I squared? We'll take that right here, this here, e to the I times pi over 2, and square it. And so when you square it, you multiply this together, and what do you get? The 2 and the 2 here cancel, and you get e to the I pi, right? And e to the I pi is -1. We just showed it. But I want you to think about a different way now. Look at this e to the I pi. What is the angle? What is the angle you rotate through? Pi. And then how far do you walk out? 1. So walk out 1, and where are you going to land? -1. This is bizarre shit, but it's awesome. You can do this now. If I ask you what's I raised to the I power, that's an imaginary number raised to an imaginary number. That's weird, right? Using this formula, what is I? It's e to the I pi times pi over 2, right? Because that's a rotation by pi over 2, move up 1. Take that and raise it to the I. So multiply these two together. Oh, wait, you square the I, right? What's I squared? -1. This is e to the negative pi over 2. That's a real number. So if you take the imaginary unit I and raise it to the I, you get a real number. It's weird. This is where things start getting really, really weird. This is all related to polar. You've seen the polar formula in pre-cal. There's a formula in pre-cal. R e to the I theta equals R cosine theta plus I sine theta. Sorry, I times. I think a lot of times they pull the R out. Cosine theta, I sine theta. In certain pre-cal classes, you get to this. That is exactly Euler's formula. But in complex numbers or complex variables, if you go on and do more math stuff, this is the one we work with, that one right there. Okay, everyone, it's way past time. Y'all have a good Thanksgiving, okay? Thank you for being here. Thanks for your participation at home. Do your homework, get caught up on everything. We have 1 week, we have 2 classes left, and then we have a final. Have I sent you all the review? I sent you all one earlier, right? Like a get you started review, okay. On that get you started one, you should be able to work through a lot of it now. Next week, we're going to do more Taylor series. I want to make sure we get through Taylor Maclaurin. And then probably Thursday will be us just trying to talk a little bit about chapter 9. So 1 more day of series, and then we get, I won't cover all of chapter 9, but I'll do some of it. All right, have a good one. Any questions at home? I see some chats. I wasn't paying attention. Let's see.
Is that what you wanted us to think about? Or
What's that?
earlier you were like, now think about this, and then you said you'd go off on a tangent. Is that what it was?
I don't think I was there yet because I needed the E stuff first. What was I no, I don't know if I'm able.
Oh, it was when you were talking about sine.
Yeah, see, I had put together a Desmos demonstration. That's kind of what I was, I think, gonna go into. I had put this together before to show kind of like the compare. Here's sine of X, here's X. And you can see that, you know, I have it calculating the difference between the two right now. And so as you get closer to 0, you can see that the difference between the two is like so negligible. You can, you know, zoom in and try and see that they are not the same, but damn, they're close. And, you know, you get in here, it's like, yeah. And then I did the same thing for the cosine one, showing this is 1 minus x squared over 2, and there's cosine. And then again, you start getting in here and trying to figure out, you know, are they close to being the same? And obviously they are. So I was going to get into this, and I just didn't want to take any more time.
Yeah.
There you go. Now you can see there's a difference.
And you're zoomed in like so far.
Yeah, exactly. But this is the thing that's weird, though. I mean, it's like, because the real numbers are the way they are, you know, that is a gap. You know, I mean, it's only negligible. It's only negligible because in the real world, we can't go that small, right? But in math, I could keep going, and the space between here and here is infinite. You know, I mean, we can measure the space. This has measure, but you could argue that there's no difference between, if you were to try and measure the number of points, right, between here and here, the number of points between here and here is equivalent to the number of points between that and if it went up to 1 billion, you know, so it gets a little weird.
So I assume, is there like if there's one half and then there's another half, like cosine and sine are like they're shifted, right?
For what are we
Is
talking?
there- I'm trying to think, say like, is there one where it's like all of those? So it's kind of like the e to the x power series, but it alternates. Is there
I see what you're saying.
something about that?
Yeah, so where it's sine and cosine together. Yeah, so the alternating part would be tricky, right? Because they both start out positive, right? So if you put them together, how do you want to put them together? That would be the
Yeah.
tricky part. Do you want to add them? If you want to add them, then you're going to have, you know, positive, positive, negative, negative, positive, positive, negative, negative. If you subtract them, then you have something else, right? But you can start doing things like that, and you'll actually get some of the identities that you have from pre-cal, like when you, right? So I'm trying to think, there's not a function that is, there, see, because there's no easy way to define how you put them together,
Yeah.
right? Add them, subtract them. Now tangent is the ratio, Now, so we need to figure out, how do you do that? And I didn't get a chance to do that today. I'll do that next class.
You go term by term, or
You go and you do division, like old school division with a division box, long division. And that's the way we do it. Yeah, and it's a little tedious.
like first term over first term, second term over second term, or what?
No, you have to do like
Oh, like long division.
long division. Yeah, long division. So it's really, it's tedious and it's nasty, because like if I take, what is tangent? Tangent is sine over cosine. So that means I'm going to take the sine one, which is x minus 1/2 x squared, 1 over 3 factorial, which is 6x cubed, right? And then plus 1 over 5 factorial, 5, 4, 6, 24. That's the one that's 120, no? 5 factorial. Let's just go with, yeah, let's just do this. Okay, so I'm taking that and dividing that by 1 minus 1/2 x squared, right? Plus 1 over 4 factorial x to the 4th, dot, 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 right? Dot, 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 it keeps going. So I go here, inside goes the x minus 1/6 x cubed plus 1 over 5 factorial x to the 5th plus dot, dot, dot. Out here goes 1 minus this, right? And then you start playing your game, and you start with the 1. You say, what do I need to turn 1 into x? So I multiply by x. And so then I multiply all of those by x. This becomes, negative 1 over 2x cubed. And then here to here becomes plus 1 over 4 factorial x to the 5th plus, there'll be more there, right? And then you subtract. So this will go minus, plus, minus. And then these will go away, but now you've got to do like common denominators, and it's not fun. It's tedious and it's nasty, but this is the way it's done. So your first term here, right? Let's just do this one. If you do that, you got to put the minus 1/6 plus the half is negative 2 plus 6 over 12. This is 4/12. That's just 1/3. Okay. So when I add those, I get 1/3 x cubed. And then the next one, I'm not even going to mess with, but it's something, right?
Yeah.
And now I need to turn 1 into 1/3 x cubed. So I go plus 1/3 x cubed. And then you go again.
And then you figure out the pattern.
Well, there's no pattern. You just keep going.
There's no pattern.
You just keep going. And so what you wind up doing, right? What winds up happening is you have to say, how many terms do you want? Okay. So how many terms of this series? Maybe there's a pattern in this. Yes, there could be a pattern in this. Or sometimes we just get like the first few terms and we say that's good enough.
Good enough.
Yeah, good enough.
Yeah, because I saw tangents not on the sheet.
It is not.
Inverse tangent is.
Inverse tangent is, and the reason inverse tangent is because we did that last time. Inverse tangent, right, is the inverse tangent is equal to the integral of 1 over 1 minus x squared dx, which we can use that, what do you call it on? Geometric series thing. Yeah, but if you want a tangent, we could probably just go to Wolfram. We could just go to Wolfram. We could say tan x series. So it gave us the first two. So I'd already done this by hand. I had the x and I had the x cubed over 3. If you keep going, you get this, more terms. So it gave you a few more.
Oh yeah, the pattern doesn't look very obvious.
Yeah, you do have odds, which means it is an odd function. It's only odds. But this might not be that easy to get. There's probably a formula, not through here, but I'm sure someone's already came up with it. Tan x series formula.
And is the reason we don't really go over that because it's just the ratio, or?
What do you mean that we don't go over that?
It's not like one of the important.
One of the common ones. Yeah, because it's a ratio. Yeah, and it's not, if you ever have to use tangent, just use sine and cosine.
Because it's like tangent's only important because we have sine. There's
Yeah,
no point to it being other way.
yeah. So in that horrible teacher video I was showing you, let's see here.
It kind of looked like, just from what I can see, like he took the 1 over top out, but obviously you don't know what he's doing. So.
Hey, I'm not sure who 1032949 is, but yeah, I see your thing about the factorial there. Okay, what were you saying, Christian? That he was what?
That it kind of looks like he just like took the 1 off the top and put it over something else, but I
Yeah, watch. I'll show you what he was talking about. Let me get to it here. Right there. Okay, so this right here, what he did, this right here. Okay, from what I can see here, this is a 1. Let me do a different color. This is a 1. And then this right here looks like it's 1 minus x squared over 4 plus 5x to the 4th over, I don't know, 192 or 172, whatever, 192. And then, so what he did on the next line, bring it back up. That's this line. On the next line, see the 1 over x, this x cubed still here. So he didn't do anything with that. What he did was he took this 1 and divided it by this. So he did 1, okay? And then out here is 1 minus x squared over 4. Let's go with this, plus 5x to the 4th over 192. Let's go with that. So now you play your game. Turn 1 into 1, 1, right? So then you put under here 1 minus x squared over 4 plus 5x to the 4th over 192. Take this row, subtract it, right? And there's nothing up here. So your first term is x squared over 4, right? And you need to turn 1 into that now. So you put up here x squared over 4, and then you play the game, right? So let's see, does his next line have that? Yeah, 1 plus x squared over 4. And then you keep going, right? So the student's looking at this going, how the fuck, like, how does this turn into that? It doesn't seem like it should, but it does, right? So when the student asks, how did you get from this line to this line? He just said, I just divide 1. Yeah, so it's a simple idea if you understand it. I mean, there's no criticism here for the teacher or the student. It's just like, I don't know who. I think he could have done better. I think the student could have done better. It would have taken, what, 10 seconds? Just be like, hey, this long division, put the 1 inside, put this part in the parentheses outside, do the,
Or just show the
Yeah.
long division, not even work it out.
not even work it out. Exactly. Yeah. But I think that maybe, this guy's old school, maybe he's like, thinks maybe he's had a history in that class of students messing with him.
Yeah, because it seemed like.
Yeah.
he thought they were messing.
Yeah, he thought, oh, you're just pulling my leg, you're just messing with me. It's hard to say. All right, cool. Yeah, have a good Thanksgiving. Questions at home? You good?